Okay, so here's a polynomial function, degree 4, has a real root of -2 and multiplicity 2. So we already know that that's going to look like x plus 2 quantity squared. 1 minus 2i is a complex root, so therefore that's going to be written as x minus 1 minus 2i. And since it's a complex root, there has to be the conjugate pair, which is x minus 1 plus 2i. So I'm first going to multiply this and distribute that negative. We'll deal with this y-intercept of 0, 5 at the end. Okay, so I just distributed the negative here. Now I'm going to multiply x times all three of these. Now I'm going to multiply the -1 times these three. Now I'm going to multiply the 2y times these three. So collecting like terms, I get x squared minus 2x. These cancel, those cancel, and left with plus 1 minus 4i squared. Since I squared is equal to -1, -4i squared will be -4. -4 times -1, which is equal to 4. So I get x squared minus 2x plus 1 plus 4, which is x squared minus 2x plus 5. And I want to multiply it by this guy here, so I'm just going to rewrite it down. So I'm going to multiply x squared by these three terms here. Now plus 4x times these three over here, and the 4 times these three here. So combining like terms, I get x to the 4th plus 2x cubed plus x squared plus 12x plus 20. Now we're given the fact that the y-intercept is 0, 5, so that means, like in previous problems that we did, we now want to figure out what is the coefficient in front of the polynomial, so I'll squeeze that in right here. Actually, I'll just move over the... So now the a has been squeezed in here, and we're given that the y-intercept is 0, 5. So that means I get 5 equals a times 0 plus 0 plus 0 plus 0 plus 20. So a equals 1/4. So that means my final answer will... And there's my final answer. With just putting the 1/4 up front, no need to multiply the 1/4 through. Next one is similar. Create a polynomial function, degree 4, complex root of 1 minus 2i and 2 plus i. So that means we have the complex pair of also 1 plus 2i and 2 minus i. And this piece here, these two pieces here, we'll deal with them at the very end. So therefore my function will be x minus the root 1 plus 2i, x minus the conjugate 1 minus 2i, x minus the root 2 plus I, x minus the conjugate root 2 minus I. So I'm going to do distributing of all the negatives here. And now I'm going to multiply these complex conjugate pairs and these complex conjugate pairs. So I'll do this one first, multiplying the x through, and multiplying the -1 through, and multiplying the -2i through. Okay, so there's all the work. We'll combine like terms in a minute. Looks like I lost a term over here. That's, okay, don't know what happened there. Those guys just disappeared. So let's distribute the x through these three terms and multiply the -2 by these three terms over here. And multiply the I by these three terms over here. Okay, combining like terms on the left-hand side, you get x squared minus 2x. Those two cancel, plus 1 minus 4i squared. X squared minus 4x, those cancel, plus 4 minus I squared. So this gives me x squared minus 2x, and this is -4i squared, so that's plus 4, so that's plus 5. X squared minus 4x, and this is +1, so that's plus 5. So now we need to multiply these two together. Okay, so x squared times these three, -2x times these three terms, and 5 times these three. Value. So we plugged in 0, we got negative 1/5. So let's rewrite the problem with negative 1/5. If we consider the end behavior model of this function here, if I was to distribute this negative 1/5, which I won't do, but the lead term would be negative 1/5 x to the 4th, which is the end behavior model. So that's what we were given. So therefore, we've satisfied all the constraints. One more problem to do. Okay, so we're given a third degree polynomial whose coefficients are real. That means there's no i's in front of the x's. The zeros are 2, 5, and 3 plus I. Is this scenario possible? Well, if we were to write out the function, we would have f of x equals x minus 2, x minus 5, and then x minus the complex root. And since the conjugate theorem says that you must also have the complex conjugate, we must also have 3 minus I. Well, by adding in that complex conjugate there, we lose the fact that it's a third degree polynomial. I've now created a fourth degree polynomial. So therefore, is this scenario possible? No, because the complex conjugate will make it a fourth root.